And I would like to thank our guest today, which is Professor Greg Wagner. And he has a long experience at the Sandia National Lab in Livermore, which is, I think, is a very important plus, because I mean the national labs in the States, I don't know them well, but they sound like very exciting, very advanced place to be. And in this lab, we started to work a lot on multi-scale and multi-physics computational methods. Then, since 2015, he joined the faculty of the Mechanical Engineering Department at the Northwestern. And there he keep exploring the multi-phase flow, in particular flows with complex and moving geometries. And I think all these knowledge are perfect for our additive manufacturing issues, where everything is moving here and there very fast. So I'm extremely happy to welcome him. I'm very glad that he accepted our invitation. And so, Greg, please, it's the floor is yours. The virtual floor is yours. Thank you.
Virtual floor. Thank you very much, Fernando. Thank you very much for the invitation. It's an honor to be able to talk to you today. I met many of you, including Fernando, in person for the first time at SimAM a couple of years ago in Pavia. And some of what I'm going to talk about today will be a review of that, but I promise that if you saw that talk, there will be some things here that are new, and also some things that may be a review of that. But it's certainly been an eventful year and a half or so since that presentation. So I hope that you and everyone there are doing well. So our motivation has stayed pretty much the same. So I don't think I have to convince most people here of the utility of additive manufacturing and why it's important. So I'll focus on what we're interested in my group. We're very interested in the effects of the process parameters on the resulting microstructure and eventually properties. And of course, this is, I think, pretty well recognized as one of the important problems. I'll highlight just a couple of examples of this. So here's some work that I like to highlight from the Penn State group, where for a directed energy deposition experiment, they ran the same build with both low and high power, and saw an obvious difference in the microstructure that results, right? So smaller grains for the low power case. And there's a resulting difference in the material properties too, right? Where the low power case, you might expect with the smaller grains, the low power case ends up being a little bit higher failure stress or higher failure strength. And there's also an obvious anisotropy because of the anisotropy of the build and the resulting structure. And it can affect not just properties, but even whether or not a particular material can be built, right? So we know that there are materials like aluminum that don't lend themselves very well to additive manufacturing. Typically, these are the same materials that don't lend themselves to welding or other things. And a lot of times it's because they have phenomena like hot cracking. So this paper from a few years ago in Nature was demonstrated that while this aluminum, a 7000 series aluminum, under kind of standard conditions under additive manufacturing developed cracks, and basically, and here's the resulting stress strain curve, essentially they couldn't get a coherent material that could bear a load after this. But by inoculating it with small zirconium particles, they were able to, or nanoparticles, they were able to get a finer grain structure. This finer grain structure alleviated a lot of the problems with cracking, and eventually then led to a much stronger material, and maybe just as importantly, actually led to a material that could be built with additive manufacturing. So these are two examples of ways in which the process can affect the properties and the buildability of a particular material. So in my group, we focus on simulations, and my background is mostly on development of numerical methods and how they can be applied to problems like this. We're looking at this problem at a few different scales, and I'll talk about a couple of these in today's talk. So we have active work on part scale modeling. So this is trying to predict, in particular, the temperature field in our case, over a build, over many layers. So think about the multiple millimeters or centimeter scales. We are also interested in modeling down at the powder or the melt pool scale. So this is now down at the hundreds of microns scale. And this is where those multi-phase or moving interface simulation techniques come in. And we also coupled those types of results to microstructure formation models. And I'm not going to talk as much about that today, but this is also an area of interest for us. So what I will talk about on these first two cases, I'm going to talk about some of our modeling techniques, but then also talk about how we're using some data-driven or machine learning methods in order to, I think, extend the usefulness of our results. So two kind of mini stories that I'm going to tell, first at the part scale and then at the powder scale. So on the part scale, we have developed a finite element model of the thermal history throughout a part. And this is a fairly straightforward model. It's just solving the heat equation in enthalpy form. And this allows us, I don't know how well movies are coming across on the video, sorry. But we can build a part, trace the thermal history throughout the part. Basically, what we're doing is tracking the same laser path in detail, right, at the kind of laser scale. So we're capturing all of the details in the laser path, the material addition. As material gets added, of course, the complexities in the simulation are that you change your boundaries and you're activating elements and things like that. But a lot of this turns out to be bookkeeping. The formulation that we're using in this case is an effective specific heat model. So we're capturing the latent heat in this case, but we're capturing it through a modified specific heat that basically has this kind of smeared out jump condition across the solidification of the liquid, the solidus to liquidus region. So the model itself is fairly straightforward. One problem with models like this, if you've worked with them at all, is validating the temperature history out of these. There are still very few ways to get detailed and accurate temperature measurements from an additive manufacturing build, whether it's the directed energy deposition or powder bed fusion process. It's hard to get thermocouples or things like that very close. So one way where this can be done, at least with some relative accuracy that takes some calibration, is through IR camera data. So we've taken advantage of this in order to try to validate our part scale models. So these are experiments that were done by basically a Northwestern grad student in a group that we collaborate with, where she built several Inconel walls, Inconel 718, 3 different size walls, or 3 different sets of process parameters at least, so different sizes and dwell times for these different walls, and used IR camera data in order to get temperature histories. So the results, by the way, Jennifer Bennett was the student who did this work. She is now an assistant professor, or about to start as an assistant professor at West Point. So this allowed us to get temperature data throughout the part, or at least on the surface of the part, as a function of time. Each one of these walls had a number of sample points, either 9 or 12, depending on the size of the wall. And so in addition, we were able to take sample specimens from these walls and measure the mechanical properties. So things like the elastic modulus. With tensile tests, we got the stress and strain at yield and failure. And UTS is one that I'll show in a few cases here, the ultimate tensile stress. So we have a number of points where we have both a measured temperature field, at least we have IR data that purports to give us a measured temperature field. We have property data at those same points. To that, of course, we can add our simulation. So we simulated the same case using our finite element code. The mesh, or representative mesh, is what you see on the left here. The toolpath was fairly simple, just a single scan wall with a layer height of 0.5 millimeter. So this is a directed energy deposition where the scale itself is fairly large compared to a typical powder bed method. And so we were able to simulate that same case. Here are some of the results of this comparison. So what you're seeing on the bottom of the slide are 8 different points, simulations for 8 different points. The data from the 9th point on the previous slide just was clearly wrong. And so for those points, a couple of key takeaways. So the dotted lines are the experimental measurements. The solid lines are the corresponding simulated temperature histories. We're matching them very well, I think, through both the build, that's this oscillating section, and then the eventual temperature decay as you build, right? It starts to cool. One other thing you can note is that the experiments are not able to capture the initial heating of each point very well. So the region through the actual melting temperature, which is about 14 or 1500 degrees K in this case, the experiments are not getting data there. And in part, it's because the emissivity of this material is changing as it changes phase, and so it's hard to get reliable data, at least in these experiments that were done here, from the melt pool or from that melt bead itself. So in a way, the simulation I think is which at least predicts that we get above the melting temperature, which the experimental data doesn't show. I think in that initial heat up region, the simulations are probably the best data that we have to work with. So if we're interested in cooling rates and things like that, it's the simulation data that we want to be able to query for that. And that's important because, of course, that's what we'd like to be able to correlate with the properties. So in addition to that, we have, at some of the points, we have SEM images of the microstructure. So this was done in collaboration with David Dunant's group here in the Material Science Department at Northwestern. Jenny Glarum is the student who has worked most extensively on this. I won't go into details of all of the microstructure, but the key takeaway or the key trend here is that at each of these cases, A, B, and C, are a different size wall. Actually, case C is the same size as case B, but with an additional dwell time, so added time in between each scan. And what we see is maybe not unexpected is that if we can measure the primary dendrite arm spacing of each of these cases from these SEM images, we will end up seeing an increase in the ultimate tensile strength. Okay, and we can look at all of the other properties too, but that's one of the main takeaways from this graph. So mostly I just want to show you that we have these images and this data. Looking a little bit more in depth at that, we can compare that with the simulation data. And again, this particular result is not so surprising. So if we look at data across those 3 cases, and compare first the computed cooling rate. So this is from our finite element simulation, these bars on the left. Everything here is normalized according to the mean. So 1.0 would be our average case across these. So across these 3 cases, the cooling rate is increasing. It's really just a result of the fact that there's a longer amount of time in between each laser pass or between each build pass at this scale. So the cooling rate is increasing across those 3 cases. The dendrite arm spacing decreases across those. And then there's a resulting change in the material properties for each of those different microstructures. So the strength in particular goes up as the microstructure gets smaller, which again is fairly well expected. So that's great. So we can use our temperature histories in order to back out a cooling rate and say something at least about the expected microstructure and properties. Things get a little bit harder to understand so those were averages over each wall. If we look at individual locations in each wall, though, the story gets a little bit murkier. Again, so if we take 3 different points in a single wall and look at their temperature histories, if you think about it, it makes sense. The cooling rate as we go, so let's see, so 0.1 is toward the top of the wall, 0.8 is toward the middle, 0.12 is more toward the bottom. Toward the bottom of the build, the cooling rate is the highest because that's where you're closest to the substrate. You're conducting heat away most quickly. Toward the top of the wall, you've already built up residual heat, so your cooling rate has slowed down. And our temperature histories predict that. We can back up. By the way, when we compute the cooling rate here, we're talking about the solidification cooling rate. So we're talking about the temperature rate of change as you pass through that solidification region for the last time. So really, it's ignoring in a way everything that goes on after that that last solidification step. And you're probably already looking at these results, and you see the trend is not so clear anymore. So our cooling rates are increasing as you move down the wall. Even the dendrite spacing, which itself is a hard measurement, is not showing this trend. But pretty clearly the strength is different in the middle of the wall compared with the other points. And this is a trend that we see across multiple walls in different locations. And so for some reason, the cooling rate by itself is not such a good indicator. It is for the points, and so let me remind you, we have mechanical testing data for all of those, order of 100 points, samples across the walls, but we only have microstructure measurements for a subset of those. And so we can see that, our predicted cooling rate tracks fairly well with the primary dendrite arm spacing. Again, as you might expect, as the cooling rate increases, the microstructure gets finer, the arm spacing goes down. But when we try to relate that cooling rate to the UTS for all of the points that we have, it's a lot harder to tell this story, right? So the cooling rate versus UTS here, these are the three different walls, three different wall cases. What we would hope to see here is that we could plot a trend line and at least up to some kind of uncertainty be able to see a slope in this data. But that slope is just really not there. And I think that the relationship between cooling rate alone and UTS is not so clear. So this was sort of disappointing. So clearly, though, there's something about the temperature history that is affecting the properties, and we want to be able to look in a little bit more detail. So what if we start to look at the rest of the cooling curve, so beyond just the solidification region? So here's a sort of simple way of looking at these correlations, and in the end, maybe not our final way, but it's a way that we can see some information. So we took each one of these temperature histories, and binned the amount of time that was spent in each individual 25K band of temperature, right? So basically, look at the region between 1000 and 1025 degrees K, count up in total how much time was spent in that band, and then plot that in against the ultimate tensile strength or any of the other properties that we measure. And again, the trends are not perfect, but there are some clear trends here that we see where the larger the amount of time spent in this kind of middle temperature range around maybe 700 or 800 to 1000 degrees K, the higher the ultimate tensile strength. And you can see some of this through the solidification region, but things are much more pronounced. This separation is a lot more pronounced during this kind of middle temperature range. Okay, so there seems to be something going on there, even if we don't have an obvious way of quantifying it. And we could speculate about, is there a phase change or some kind of precipitation that's happening in that region that's being caused by the amount of time at that temperature regime. But in order to actually take a temperature history and do more than sort of wave our hands at it and try to see what's going on, we wanted to do something a little bit more quantitative with this. So we took these temperature histories and fed them through a neural network. And in this case, a 1D convolutional neural network, or CNN. And what a CNN is good at is picking out these features, these sort of hidden features that might not be obvious, or at least be hard to describe quantitatively in some other way. So each one of the CNN blocks is taking this data, reducing it to a number of features, and trying to pick out through these individual filter channels, trying to pick out the features that end up being related to the UTS. So the output of the CNN, I'll show this in a second, the output of the CNN are these features. Then through a fully connected neural network, we're relating this to the ultimate tensile stack. Okay, and so, we can look at these individual features in the CNN and again, see what the, what is it that this network is picking out and relating to the UTS. And if we zoom in on a couple of these, there are really two features or two classes of features that seem to be pulled out of this. The first, this one that's labeled fourth here, is something that is important at these early times when this material is in the melting range. Right? So there's clearly something important about this solidification range, which is not surprising. But there's also another class of features, the seventh feature, that's being picked out that has something to do with how much time is being spent in that intermediate temperature range. Okay, and again, exactly what that is, this CNN can't tell us, but it is telling us that there is a clear correlation between that feature and the UTS. And if we train our network then using that data, so the training data, which we expect to be good because we're sort of fitting this, is a good match. But if we take that model then and apply it to the test data that we've set aside, we find that now, unlike that cooling rate prediction, our predicted UTS is actually very good. We are predicting, if you're not used to looking at plots like this, it's the predicted UTS from the model against the measured UTS. You want to see everything lying on a straight line. And we come fairly close up to what I would say is probably our experimental uncertainty. And so it's hard to do too much better than that. This, by the way, is largely the work of my student, Li Xiaofeng, who is working on the publication of this data. So more details to come in exactly how we're setting up this network and testing the data. So this is sort of our story on this part scale model. So just to summarize this, our goal, of course, in everything is to link our computed thermal histories in some way to the experimentally measured microstructures and properties in order to build models. We're finding that machine learning, more than our more traditional methods like looking at cooling rates, machine learning is able to uncover some of the important features in this thermal history that correlate with the thermal properties. And now the challenge, I think, is to take those correlations and try to use them to yield insights on what physical mechanisms are causing that. And we know that a traditional T curve or something for this material may give us information about precipitation or precipitates that form in that region. But AM material having a different thermal history may look different from a typical TTT curve, and so this is often insights that are that only this type of analysis of the data can give us for this AM type of material. And so that's the goal now. And of course, the goal is to be able to take this tool and use it to optimize processes and design process parameters such that we can optimize the eventual properties. Okay, so let me say then a little bit more about some of our powder or melt pool scale models. And some of this, again, if you saw my talk a couple of years ago at SimAM, this piece of things will be a review. But since then, I think the publication has come out, and so you can look at some of this data. Again, I'm not sure how well these videos come out, but this is the sort of thing that is motivating many of our simulations. So this is work done by our collaborators here at Northwestern. This is actually using the Argonne National Lab Advanced Photon Source to gather high-speed X-ray data. This is of a DED process that, let me go back and start this over if I can do that. In this case, the powder is being injected and not blown at a high rate, but you can see a couple of things here, that there are interactions between the powder and what is clearly some kind of vaporization plume coming from the melt pool. So these powder particles are getting entrained in the vapor. And so there's this clear interaction between the melt pool, the surrounding vapor, and the powder that's being injected. These are all things that we'd like to be able to understand. One interesting phenomenon, again, these are our collaborators in experimental group here at Northwestern. One interesting phenomenon that was found in similar experiments was that sometimes powder particles are clearly not just blown away by the vapor plume, but once they get kind of entrained in the laser itself, they seem to move in the direction of the laser toward the substrate. And there was some discussion over what's going on here. Why does this particle all of a sudden change directions as it moves into the laser? And finally, what we realized is that it's all coming from the vaporization force on this individual particle, right? It's like setting off a little rocket tail, a comet tail on this particle as it enters the laser beam. The top side of it is evaporating. You're getting a vaporization pressure on the powder particle, and that's then driving it. I should have said here that the time is moving from right. So upper right is the first panel, moves to the left, and then wraps around down to the lower right here, and then to the left. So I'm not sure why these were plotted in this direction in the paper, but hopefully you can track where this particle is going. It goes up and then gets driven down by this vaporization plume. So we've developed models and multi-phase simulation techniques that allow us to simulate this sort of moving interface with evaporation problem, both at the powder bed scale for powder bed fusion problems and for DED problems, where we can look at the injection of powder particles and their interaction with the laser and with the melt pool. I'm going to spend a few minutes on the formulation for that and some of the results. So we are solving the full Navier-Stokes equations. I don't like to show too many equations, but I want to be able to at least point out some of the modeling choices that we've made here. So this is I'll go into a little more detail on the next slide. We're solving a level set, diffuse level set equation in order to track the moving interface. So we have a surface force, a continuum surface force in this case, that represents forces like the surface tension force, Marangoni forces, and the vaporization forces at that melt pool. We have a penalty term in the solid region that constrains the velocity to zero. This is a fairly common way of handling these kind of solid to liquid phase changes. Gravitational forces and evaporation forces then at the surface themselves. In our continuity equation, we're assuming that our two individual phases, metal and gas, are constant volume, but at the surface itself, we can have evaporation, and this leads to a volume change right near the surface. And so this is where this additional source term, instead of divergence of u equals 0, we have a divergence of u equals that volume change that's happening at the surface. To that, we can couple our thermal evolution problem. So again, now we're solving the heat equation with convection and phase change. So we have a liquid fraction term that's capturing the phase change. And again, we have an evaporative heat loss at the surface. Again, this formulation has now been published in CMAME last year and is largely the work of my former grad student, Stephen Lin, who's now at Sandia National Labs. We're tracking the moving interface using a level set formulation. I want to keep an eye on my time a little bit to make sure I don't fall too far behind. And we're coupling that in order to well conserve mass. We're coupling this to a volume fraction evolution equation that, taken together with our level set, allows us to improve the mass conservation or the mass losses that you often get in a level set formulation. So the level set itself we're using to maintain a signed distance function, and to be able in particular to compute normal vectors, which is hard to do from a volume fraction equation. The volume fraction evolution equation is then solved separately, and that's what's getting used to actually enforce the local conservation. So we didn't invent this technique. There are others using a combination of these two equations in order to conserve volume or mass in level set formulations. But we've kind of modified it for our or unstructured mesh problem, especially for a case where we have where we want to enforce a balanced force algorithm. So our algorithm looks something like this. We solve that level set equation. We get a provisional set of normal vectors. We use the normal vector then to solve for the volume fraction. So I'm going through this a little bit quickly, but I want to give you a sense for the algorithm. Then we use that updated volume fraction to redistance our level set, and we end up with then a recalculated normal vector at each point. And those are the normal vectors then that we can use in order to compute things like surface tension and the evaporation forces in our thermal and fluids problem. So finally, we solve for the fluid temperature. One more equation that we add to this, we realized that trying to capture the source term with, we weren't able to implement in our parallel code any sort of ray tracing method in order to track the radiative transport. What we modeled instead was sort of a one-dimensional radiative transport, not one-dimensional, unidirectional radiative transport equation. We wanted to capture effects like the shadowing of particles, right? So if you have a laser that is incident on a powder particle, you want to capture the fact that the substrate underneath it is going to be shattered. Whether that powder particle is flying through the space above the substrate or is actually sitting on the substrate. So we're solving for in laser intensity field that can be absorbed at the surface of either a powder particle or the substrate. And that gives us this shadowing effect automatically. All right, so finally, the interface treatment and the fact that we're coupled to this surrounding vapor allows us to capture at least a little bit of this vapor plume that you get near the evaporation region. So the recoil force at the surface is giving us this keyhole-like behavior at the surface, and the coupling to the surrounding vapor through our continuity source term is giving us the vapor plume. So we can look at the combination of these and the interaction of these things. So we can use this type of model to look at individual phenomena in, say, a directed energy deposition. So let me show a short example, or a couple of short examples of sorts of things we can do with this, sort of as a proof of concept. So we've simulated a moving laser on a substrate and looked at the injection of powder particles above this, not quite at the powder number density that you have for a full DED simulation, but to be able to test the effects of individual powder particles and the phenomena that we see. And we're able to look at this effect that I mentioned with a powder particle getting entrained in the laser. So again, apologies if this is not coming well across the network, but for 3 different particle sizes, we can look at the interaction of that powder particle with the laser and see how the different effects of the laser, the vapor plume, are causing the changes in this trajectory of the powder particle. So again, only for the smallest particle size does it eventually get completely entrained in the melt pool and subsumed into the melt pool. Another thing we can look at is the effects of the melt pool, of the particle shadowing on the melt pool. And this again is something that was seen in those high-speed X-ray videos, where often a powder particle will kind of occlude the laser and leads to a reduction in the vaporization, or a reduction in the keyholing in the melt pool. And we see something exactly that. So again, in a time sequence, as the powder particle moves into the laser, it causes a decrease in the temperature here in this region number 2 that again reduces the evaporation, reduces the temperature, causes the keyholing to be lessened there a little bit. Once the powder is then entrained into the laser, then the keyhole will start to reform and we'll start to get that evaporation again. And this is, again, a phenomenon that's been seen in our experimental videos. Okay, so this is a tool that we've developed for the melt pool, but in fact, it's hard to take that information and use it directly in, say, a part scale simulation, right? How do you use this in order to design a process, especially given that there's so many effects that are coupled between what's going on at the melt pool, what's going on in your part geometry and your temperature transport, your heat transport there. And this, I think, is still an open question in much of the modeling for AM, is where is the coupling between our fine scale melt pool models and the part scale models that one might actually want to use to design a better process. So we are interested in figuring out, how do you account for those melt pool details in the part scale solutions? So how do you take what we've done at that fine scale and then build it into our directed energy deposition code? What I'm going to show is sort of a first step along these lines, and it's definitely not the full answer to that. I like to think of this problem in two ways, or as two separate subproblems. One is the fast prediction of these melt pools, right? So we want to be able to take the data that we've developed through our melt pool simulations and use that to come up with reduced order or fast models to predict the melt pool temperature or velocity. And the second is the coupling itself, and how do you build that in? So we have active work on the second of those problems, but what I'm really going to show is the first piece of that. How do we take our melt pool data and use it to develop reduced order models for that melt pool velocity that then we can further couple to our part scale? And so for this, I'm going to fall back on the machine learning approach. This, I want to call out in particular my postdoc, Lin Chung, who's been working on this. And he has developed, this is largely his brainchild, what we're calling a RivNet, a representative volume element neural network. And this it has some things in common with things that you might see that are physics-informed neural networks or other types of neural networks. The difference here is really that it starts with an image-based representation of the input fields and uses a convolutional neural network through an encoder and a decoder in order to relate the hidden variables. So, this is described here, and I understand this sort of a high-level way, but I want to get the main idea across. So the inputs, this is a case looking at just the strain field in a composite that's made up of particles. This is not an AM problem, not an AM process problem, at least. The inputs, though, are representations of your microstructure in this case, and also some representation of the load condition as additional parameters. So this is like a voxelized or pixelized representation of your microstructure. The output, the goal of the output, are the strain fields in this case. And those strain fields then get fed into various manipulations that allow us to evaluate a loss function. The loss function can be some combination of physical principles. So do you satisfy the equilibrium equation, the expected stress strain laws here? Or experimental data. Do you get something that matches your data, or a combination of those two things? So physics and experiments can all be built into that loss function. And the magic happens in this RVE layer here, or this FCN layer, the fully connected deep convolutional network that takes this encoder. My simplest description of this is we're looking for those hidden variables in both the inputs and the outputs that can be correlated to each other. The hidden variables that you would not be able to pick out by hand, but that the CNN is good at recognizing. And this has been demonstrated, and so this is a work that will be submitted very soon, demonstrating this for some solid mechanics problems. And we've recently demonstrated this as well for our melt pool simulations. And these are melt pool simulations that we can train using our fully detailed melt pool simulations, feed them into this network, and get a prediction for later temperatures and velocities in the melt pool. So in this case, and again, just very high level of detail here, the inputs are the temperature field, in this case, temperature or velocity at some initial time. An image representation of the build path, and an image representation of the heat source field, so the laser spot, for example. And the outputs are a series of snapshots of the temperature field at later times. And again, these are all being related through this encoder-decoder network. And the loss function in this case is the differences with the training data that comes from our detailed simulations. So let me just show, let's see. So the ultimate strategy here is to be able to replace our detailed simulations with this neural network evaluation, and then couple that neural network evaluation with the surrounding temperature field in a part scale model, right? So this is our kind of the notional diagram of our eventual strategy. Let me show you some preliminary results of of both 2- and 3-dimensional melt pool simulations, and that's where I'll quit. So in 2D, it's a little bit easier to see the training process here. So we have some 2D heat equation simulations of the moving laser beam where we have, essentially a melt pool, laser spot. This red box is showing kind of our representative volume region, where over this region, we're sampling data over a given amount of time. And that includes both regions where the laser spot is moving in a straight line, where it's turning. We can vary the process parameters and the scan speed and the half spacing and things like that in order to gather as much data as possible from these simulations. And our goal, like I said, is to predict, in this case, the temperature at a later time. So this is showing some of the results of that. So after training with some of this data, the training stage, by the way, takes about 20 minutes to train the neural network. That's not including actually running the simulations themselves. But these validation tests are showing that, okay, so this middle row here are what we treat as our ground truth, right? This is the simulation of the heat equation. Our fast evaluation is giving a temperature field that well matches that simulation result, but it's doing it at a very small fraction of the time, right? So in this case, 1,000th of a millisecond for some of these, and we can achieve that through the parallelization of this, right? So we're solving multiple instances on GPUs in this case. In 3D, we're doing something similar. And running our detailed simulations for different laser tracks. So this is a case where we're not tracking all of the moving interface. We're assuming that the interface stays fairly flat, but we are still solving now for the convection in the melt pool and the other physical phenomena at the melt pool. And we're running with a range of different laser powers and scan speeds that would be significant for a typical powder bed process. And we can increase this, the range of process parameters. And we're getting temperatures and velocities for each of these and using these to train our simulations. And this is what the results look like. And again, these are just preliminary results, but overall, we're really happy with this. So for a given melt pool, we can predict. So if the ground truth on the left is the simulation data, the neural network prediction given on the right for a time 20 or so time steps later. Not perfect, but matches the temperature and velocity very well for a particular melt pool size. And again, we're working on testing this out for different cases, improving the amount of data, and eventually coupling this to the full part scale simulations. Each individual melt pool prediction, and this is the key, can be done in a handful of milliseconds. So this is extremely fast. All right, and so that's where we are on that machine learning piece of things, and that's where I'm going to stop. I think I'm a little over my allotted time. So the key takeaways that I want to summarize here. So I think that detailed physics simulations combined with machine learning are potentially a way to get fast and accurate predictions of these process structure relations. And that can be both through analyzing the data of the results themselves, or potentially through coupling our or training reduced order models with our detailed simulations in order to give fast simulations that we can eventually use for coupling or for process design. this approach to coupling is and like I said, also an area of active work for us in trying to figure out, now that you have that information at the melt pool, how are you coupling it to the part scale model? And of course, the ultimate goal is to be able to take those fast part scale models and to use them to design better processes and to optimize ultimately the properties of the resulting material. So I'll stop there. I want to call out a few of the people who worked on this, in particular Lin Chung, who is on the job market and who is the main mastermind behind this neural network method that I talked about. Li Xiaofang and MJ Sarfi are current grad students who have worked on the part scale simulations and the neural network to predict properties. And Stephen Lin is my former student who did a lot of the melt pool modeling work. You can see other collaborators and funding sources listed here, but I think I will stop there and take questions. Thanks again for your time.
Thank you very much, Greg. Very, very interesting and exciting presentation. Thank you, really. So I would open the presentation for questions. Maybe you can write in the chat that you wanna ask a question. I see already one from Can. So
yeah,
Can,
yes.
you can turn on your microphone, your camera, and proceed. Please.
Yes, thank you for this nice talk, first of all. So my question is about the first part of your talk, where you looked into this part scale simulations and experiments. And your data-driven approach basically indicates a strong correlation between the, let's say, the collective thermal evolution between the liquidus and solidus and the UTS. And so my first question is that, were you able to discover the physical mechanism behind this? And connected to that, so I certainly understand the impact of, let's say, dendrite morphology on the UTS. But what about, I would think, a secondary effect that would have an impact on the UTS would be the volume fraction of the solid state phases. So therefore, do you think the solid state phase transformations, which are happening below the solidus temperature, are also have an impact on this UTA state? And why not, if that is an effect, did not came out in your data-driven correlation or indicators?
Yeah, thanks. Great question. So I agree, and I guess I would say that I think that this did come out, and so I agree that the secondary phases and precipitates post solidification, the solid state phases, are playing a key role. Your question, have we discovered the mechanism? I don't think we have found exactly the smoking gun of exactly what is the phase transformation that is leading to this change in properties. But I would argue, let me see if I can share again this slide. This sort of is our takeaway, I think, on why the, I've lost my sharing button. Why the solidification cooling rate itself was not enough to explain the change in the UTS, right? And I think that's exactly what you're saying, is that
Correct.
There is something going on that is post solidification. So something that seems to be related to the time that is spent in this, 800 plus or minus 200K region. And the speculation, this is what we haven't been able to identify from the micrographs or from existing TTT curves, exactly what's going on here, in what particular precipitate this might be. But I think you're exactly right, that this is an indication that there's some sort of solid state transformation that's happening, driven by how much time you're spending in that intermediate regime that is causing the change in the UTS.
Okay, thank you.
Okay, thank you very much, Ken. Are there other questions? I have maybe a couple. Greg, at the beginning, also the slide you were showing, there was all these peaks at the beginning, so very, very high temperature, and this was also the part that you were not able to capture with your simulation. Now, I was wondering, clearly, you are interested mainly in, you know, in the range where it's, you know, you're in the solid range, because if you want to capture, you know, really the effect on the material. But is there any reason why you were not really able to capture that? It's a computational issue, like dimension element, time integration that you're using, or so what are the reasons? Because exactly that's the slide.
Okay, so first let me make sure we're talking about the same thing. So maybe let me blow up so it's a little easier to see. So the dotted lines are the experiments and the solid lines are the simulations. Right. So I would argue it's the experiments that cannot capture the high temperatures above the melting temperature. And this is where, you know, I think the main reason is probably that the IR camera is calibrated for the solid. This calibration depends heavily on the emissivity of the material, and the emissivity just doesn't stay the same through that phase change. I think that's part of it. Part of it may also be just the ability to resolve that melt pool volume there. Now, that's not to say that I fully trust the simulation, especially in that very high temperature region. But, you know, there are other things there, like what are the effects of boiling and things like that right near the melt pool, especially at the highest temperature regime, where, you know, we're probably not getting perfectly right, but I'm a lot more confident in it as we get closer to the melting temperature, especially on later passes. So like I said, probably imperfect, but better than the experiment and the best we have to go on for predicting.
Clearly, let me make a comment. You're not supposed to complain about your camera, because the movie were so incredible. So already, you know, what you are showing from the experimental point of view is really beautiful. So
yeah,
you can do always better with experiments with the numerics, but I mean, already the experiments you're performing are really interesting.
It's a poor artist who blames his instrument, right? Yeah. So and a poor experimentalist who blames the camera. You're absolutely right, and I can't take credit for these experiments. It's our collaborator Jennifer Bennett who did a lot of this, and I weighed trying to show the movie of the development of this itself, and they seem to be too long. But you're right. The fact that we can get this sort of data at all, I'm extremely happy with and thankful to my collaborators.
I see other questions popping up, so I stop with my questions. So Stefan Kollesberger is looking for a couple of questions. Stefan, please.
Sure. So the one actually connects to the follow-up question, so I'll ask the other one first. Greg, I just walked out of a review of a proposal that we submitted to a large group, and we got all criticized. We suggested you as a reviewer actually, but you weren't picked. But the thing is, it was all microstructure driven. Say you know, they had cellular automatum. We had in there to compute the microstructure and phase field models, and, you know, atomistic simulations and Lattice-Boltzmann methods, like very small scale, complicated phenomena methods to then try to steer the microstructure. And the fundamental critique that these reviewers had is, what do you care about the microstructure? Because later you do heat treatment and then the microstructure is gone anyways. And I'm still pissed off at the remark somehow, because the entire proposal was based on predicting sort of upwards. And I think we failed due to these remarks. And I'm wondering what I should reply the next time.
Yeah, I am familiar with this sort of criticism. And, you know, in some ways there are points to this criticism that your as-built microstructure is not always, or maybe not even often, I would argue with that, I guess, but often not your final microstructure. But it definitely has an influence, right? At the very least, if you want to know what kind of heat treatment to do for your material, I think you need to have some sort of understanding of what your initial conditions are on that heat treatment. And what a lot of the experimental data, I think some of the nicest work on this, on Inconel at least, was done at NIST, where they've looked at the composition and the microstructure of AM materials and found that it's very different from what a nominal material might be, right? There are higher variations in all of the subcomponents and things like that. And that variation is going to drive a much different eventual microstructure, different precipitation, things like that will happen during heat treatment than you would get with a traditional wrought material or something. So I think that's my usual, that's my answer to that type of question. I mean, is that
I tried to argue hot cracking and the failure during the process and all these things, but it wasn't accepted. So so I was wondering what your instantaneous response would be. And the second one is also a question that's not a critique in your work. It's actually what I wanted to do also, and what I think many people want to do is this upscaling or say in terms of time to increase the speed of computations using neural networks, because they're so attractive in training complex functions. And I think it follows up to the question of Sergey. Massimo and I looked also into other types of reduced order models quite some time ago. And we were wondering, and I think this thought hasn't left me, you train such a model such that you can answer a question fast of which you already have the answer to. and I, so the question arises, how robust are these models when you start tweaking parameters? And so the concrete question is, have you considered having these, like laser power or stuff as input parameters to your neural network, such that maybe you get robustness out of this or not? And then the fundamental question is like, okay, now you have trained such a model, what do you do with it? Can you?
Sure, yeah. So I think the flaw, not flaw, but the limitation of these machine learning models is that they're very good at interpolation, right? But should not be trusted at all for extrapolation. So I think that you can answer questions that you have not already run, but you want to make sure that you are probably within that parameter space, at least, that you've tested for. And that, I think, is what we're finding. If we want to be able to predict with a laser power of 300, if we've done 275 and 325, we may be able to trust our interpolation in between there, but not if we've only done 200 and 250, for example. Mm. I think that's, so for the first part of your question anyway, that's what I think we get out of this, right? It's not necessarily a problem that we've already solved, but it's in the
smart way of interpolation somehow.
Yeah. And as for different parameters, yeah, I think that this is why we're running with different laser powers and different speeds and things, is we're trying to
increase robustness.
Yeah, exactly.
Okay, I won't hold other questions back, but thank you for your time and answering them.
Yeah. Thank you, Stefan. So there is another question from Sergey Belousov. Please, Sergey.
Yes. Good evening, everyone. Thank you for the beautiful presentation. My question is along the lines of the question from the previous speaker. So you showed in the last part of your presentation the neural model that predict the mel pool at the later stage during the single track scan, using the initial state of the mel pool as input. Yes, and you showed particular, I don't remember, 23 times. Maybe you can show the slide.
Yeah.
One of the last slides.
Yes. Sorry. Okay. I think
I guess. Just give me a second. Yeah. So so my question is, how far can you go from the initial state. So here you go by some time, 23 time steps. So in your experience, how far can you move away?
Yeah, I don't know a full answer to that, and whether there are, my guess is that in some cases it works well to push farther. I'm going to guess that, like I said, this is largely the work of Lin Cheng, my postdoc, and I'm going to guess the reason that he showed time steps of this size is that if he pushed it too much farther, it probably didn't look as nice. So I don't have full evidence for this, but I'm guessing, I think this is probably for what we've done right now, the limit. But what I'm interested in doing is now taking this, and this is how, you know, this might start to fit into a multi-scale model, is if you predict, what happens if you sort of bootstrap this, right? What if you predict ahead 20 time steps and then, you know, sort of rerun this through your model again, maybe with some adjustments in order to respect the coarse scale model? Can we go another 20 time steps? And I think, by the way, that this delta t is the delta t that we're using for the fine scale simulation, you know, so still a very short con.
Yeah,
but enough to propagate over some distance at least. Yeah,
okay.
so I don't know the full answer to that, but I think the vision is sort of to use this in a chain.
Okay, thank you. Just one more,
Sure.
if I may. So actually, so here I think what's important, what might be important, is that, for example, in a powder bed, you have a certain stochasticity related to the powder bed. Yeah, and here, for example, here I think it's shown something like, you know, quasi-stationary solution. So when we start, then we scan the track, and we have this stable quasi-stationary solution. But when we have powder, or we have some features, like if we scan the part, we are near the wall or near the edge. So there are some things that maybe might be hard for neural model machine learning to predict. So it's not question, it's just, you know, I thought.
Yeah, it's a good point. We definitely haven't solved that yet at that level of building in powder scale stochasticity, and whether that would, the neural network could pick that out. It's an interesting question, right? So you could imagine that that leads to some level of uncertainty in your prediction, and as long as you understand that uncertainty and can build that into your model, maybe there's a way to predict that. But yeah, we certainly haven't solved that. It's a good point.
Well, thank you.
Hi, I have also a question, Greg. Actually, two again. Sorry, very short. The first one is about why do you need the latent heat in the part scale model?
Yeah, it's a good question, and I've heard many people who have spent more time with it on the part scale saying that they don't find that it makes too much of a difference. I guess in our case, you know, our model was originally developed for cases where we cared both about simulating, you know, large parts, and also for cases where we were zooming in and looking at smaller numbers of tracks and looking at shorter timescales. And so in those cases, I think the latent heat does have an effect. I think it's been a little while since we've run this comparison. My suspicion is that the change in the latent heat would still affect the you know, the temperature peaks near the laser itself, near the spot size, and probably would not affect very much, you know, the things that might affect, say, residual stress, which, by the way, we're not predicting in our model at all. But my sense is if what you care about is residual stress, say, you probably can ignore the latent heat and just average over that. But I think there's reason to think that it might be less consequential than.
Yeah, I got the point, but exactly because at the end, what you are looking at, if I understood correctly, is more the time that you spend above a certain temperature. So if with the latent heat you capture very well the peak and maybe the shoulder in the temperature distribution in the cooling. But at the end, you look at how much time you spend above 600 degrees, for example, then maybe is in this case, the overheating that you need to see with your model is not really affected by latent heat.
That's a good question. Yeah, I suspect it still has an effect on the solidification cooling rate. You know, so that's the time that you spend right within that solidus to liquidus band. But I don't have recent evidence of that, and that's something we should go back and rerun and see how much that affects our results.
And the second question is also very quick, related with the question of Stefan and Sergey about your coupling with the RVE neural network. You say that you need a certain windows, no, to train your network, and within that windows you are reliable once you have trained it. And there are some input parameters like laser scan path, laser power, laser speed. But what about the geometry of the part? Because at the end, if you are start to print, for example, lattices, the geometry, so the part scale will affect the initial condition of your local scale. And right. That, in my understanding, is not straightforward now to include in a neural network. So you can comment on this.
Yeah, that's a great point. That's where, and this is still sort of an open question, I think. But this is why we're trying to, I didn't dwell on this detail. This is why we're looking at different amounts of initial heating or different initial temperatures for the detailed simulation. So if you hypothesize that the main effect of your part scale geometry is to change what that initial temperature is, right? Or maybe some local temperature mean and gradient, then you might hope to be able to run your neural network model or train your neural network for a range of those. And that's then where the coupling could come in to the part scale, is your part scale model is telling you what that initial temperature might look like.
Thanks.
Okay, thank you very much, Greg. First of all, since it's more than 1 hour, I would try to close this seminar. So thank you really very much for the presentation and for accepting the invitation. Thanks to everyone for the interaction, and looking forward in a close future for the next seminar.